Hello everyone. We introduced last time the idea of a continuous random variable. And we started by thinking that we measure the times some athletes finish the triathlon. The data is represented on a histogram. So on the y-axis we have the frequency density, and these are the minutes. Now here is the graph with the width of an interval being 2c from 6 to 8. Remember from histograms that the area of a rectangle is the frequency. So the base times the height give me the frequency. The probability is a frequency density. Now, if we take smaller intervals, it's exactly the same data. The graph will kind of preserve the shape, but will look more and more towards a continuous function. So time is measured discretely because when we record times, generally we record it in seconds, but not in decimals of the second, fraction of seconds. But if we think of time, it grows continuously. So if we would be able to measure exactly the data and put it on the graph, that would be the graph. This graph is called a probability density function. Probability density function. And it helps me calculate probabilities using the data represented here. Like for example, between 6 and 8, probability of x, where x is the time. So probability of x being between 6 and 8 is the black area. Remember from pure math, to calculate the area, we calculate integral from 6 to 8, f of x dx, where f of x is the rule for this graph. It is generally given. So to calculate probabilities for a continuous random variable, we calculate integrals or we calculate areas. In some cases, the function might be simple. For example, your probability density function might be this function. So if you want to calculate the area, let's say between, 4 and 6, it's the area of a trapezium. So you can use the area of the trapezium instead of integration, which is exactly the same idea. Or if your graph looks like this, for example, the probability density function, if you want the probability of x being between, for example, 0 and 3 is the area of a triangle. So if the area is familiar, you use the concept of an area. If it's not a familiar graph, then you use integral. Now, not all functions are probability density functions. Probability density function. So for a function f to be probability density function, remember it represents probabilities. F of x needs to be bigger or equal than 0 for any x, and integral from minus infinity to plus infinity f of x dx needs to be 1. The integral represents the entire area, so the sum of all probabilities need to be 1 or 100%. These are the two conditions for a function to be probability density function. Let us look at these functions. Which one could be probability density function? If we look at this first function, f of x is always bigger or equal than 0 between 1 and 3, correct? Yeah. And the area under the graph must be 1. It's an area of a triangle, so its base times height over 2 is 1. So this one is a probability density function. Let us look at the second one. If you look at the second one, here f of x on that area is smaller than 0. So it cannot be a probability density function because of this part here, which is smaller than 0. For this function here, it's f of x is bigger than 0 on both branches, correct? And the area is base, which is 3, times height, which is 1, over 2 is not 1. Therefore, it's not a probability density function. Here, for this one, f of x is always bigger or equal than 0, correct? But if I'm looking in the area, well, here is minus 1, here it's 1. Look at this. This triangle has an area 1 over 2 and this triangle has an area 1 over 2. Both are 1, so this area is bigger than 1, so it's not a probability density function. In some cases, we need to calculate the integral. In others, we don't have to, like in these examples. Okay, take some time to read this question. You can stop the movie. A. Is it a probability density function? F of x equals x over 2. Well, being a simple function, I know its graph. So let me graph it. Y equals 1 over x over 2. It's a line going through the origin with a gradient 1 over 2. And is defined between 0 and 2. F of 2 is going to be 1. So that's your function. Yeah? Elsewhere, it is 0. Is it a probability density function? As you see, f of x is bigger or equal than 0 for any x. Actually, for any x real. Because in fact, for x bigger than 2 and for x smaller than 0, the function is 0. Right? The probability of x being smaller than 0 is 0, so that actually is your function. So f of x is bigger or equal than 0, correct? And area is, it's a triangle. So base is 2 times height is 1 over 2 is 1. So probability density function, yes. Of course, to find the area, if the area was not known, I do integral from 0 to 2, x over 2 dx. And of course, I'm going to get the same one. So it's x squared over 4 from 0 to 2. 4 over 4, it's 1, minus 0, it's 1. So of course, it's the same one. But my point here is, if it's a known function, like a line, don't complicate yourself. B. If it is, then find probability of x smaller than 1. Well, 1 is here. Probability of x smaller than 1 is this area. I can just find it by looking at the area. Base 1 times height. If x is 1, x over 2 is 1 over 2 over 2. So it's 1 over 4. Therefore, probability of x smaller or equal than 1, it's 1 over 4. Of course, you could have done integral as well. So integral from 0 to 1, x over 2 dx. It's x squared over 4 from 0 to 1. So it's 1 over 4 minus 0, the same 1 over 4. I use the second method only when the function is complicated and I can't find the area from the graph. The next question we're going to ask is how we find the mean and variance of a continuous random variable. Let me remind you that for x, a discrete random variable, the expected value was sum of, and we multiply the probability of x being x with the value of x. So multiply the value times the probability, and we added all of them. Now you learn in integration, in pure maths, that if you move the sum, if the intervals become smaller and smaller, so we move from discrete to continuous random variable, then the expected value of x will be, and the sum, remember Riemann sums, become integral x times f of x, and f of x is actually the probability, dx. And that's a formula from minus infinity to plus infinity. Yeah, but again, the function might be 0 towards minus infinity and plus infinity, so you take the domain given. So that's the formula for expected value of x. So instead of having sum, we have integral x times the probability. Similarly, for the variance for discrete, we had the variance of x, remember, was e of x squared minus e of x squared. And we have already the mean. We have it here. E of x squared, remember, was sum. Instead of taking the value, we take x squared. So we multiply the probability times the value squared. Now, if we move from here, from x discrete to x continuous, of course, variance of x will be the same, e of x squared minus e of x squared. So the mean of the squares minus the square of the mean. But now, if we move to continuous, the first one will be integral. Similar with going from sum to integral, we are going to write here integral from minus infinity to plus infinity, probability, the probability of f of x times the value square. So the value square times f of x dx minus, and remember the mean was integral x f of x. We found it above and we square the entire interval. So we would just remember that this sum becomes integral and the probability is actually f of x. Let's try this question. You can pause the movie and try it yourself. F of x equals k x to the power of 4 for x between 0 and 1. Actually, you'll see very often define it as f of x equals a piecewise function kx to the power of 4 for 0 less equal x less equal 1 and 0 elsewhere. Meaning that for x smaller than 0 or x bigger than 1, it is 0. There's just another way to write the same. Find the value of k. I know that f of x is a probability density function if f of x is always positive, and after I find k, I'm going to show that it is, and integral from 0 to 1 kx to the power of 4 dx needs to be 1. Therefore, kx to the power of 5 over 5 from 0 to 1 needs to be 1. So k over 5 minus 0 needs to be 1. So k needs to be 5. So your function f of x is going to be 5x to the power of 4 for x between 0 and 1. And as you see, it is always positive, so it's a probability density function. B, calculate the mean and variance. We know that e of x is integral from 0 to 1 x f of x dx. It's in my formula booklet. So integral from 0 to 1, 5x to the power of 4 times x dx. Integral from 0 to 1, 5x to the power of 5 dx. So it's 5x to the power of 6 over 6 from 0 to 1 equals 5 over 6. And that's a mean. Variance, for the variance, I need e of x squared first. So e of x squared is integral from 0 to 1 x squared f of x dx. So it's integral from 0 to 1, 5x to the power of 4 times x squared dx. It's integral from 0 to 1, 5x to the power of 6 dx equals 5x to the power of 7 over 7 from 0 to 1. So it's 5 over 7. Therefore, variance of x is going to be e of x squared minus e of x squared, which is going to give me 5 over 252, or 0.0198 to 3 significant figures. However, you know that in order to get your final answer correct to 3 significant figures, if you want to work with decimal, you are going to take at least 4 significant figures. So 8, 4, that's my working answer. However, my final answer for this question is going to be this one. Question C says, okay, let's look at question C here. And question C says, CI. Find probability of x smaller than mu. And that's probability of x smaller than, if I look at mu, it's 5 over 6, or the expected value. So it's going to be integral from 0 to 5 over 6 f of x dx. So it's x to the power of 5 from 0 to 5 over 6 is going to be 5 over 6 to the power of 5, which is 0.502 to 3 significant figures. Next one is find probability of absolute value of x minus mu smaller than sigma. Now variance is this one. So sigma is going to be square root of 5 over 252. And indeed in my calculator, I prefer to put 5 over 252 instead of the decimal number, because then I'm going to give a number closer to the exact one. So my calculator gives me square root of 35 over 42, or as a decimal, 0.140859. So it's going to be 0.141 to 3 significant figures, but because I'm using it in a subsequent answer, I'm going to take more decimal places. Now let's see what means absolute value of x minus mu smaller than sigma. From pure math, remember that is between x minus mu is between minus sigma and sigma. Or if you add mu to all sides, you get mu minus sigma smaller than x smaller than mu plus sigma. So you're asked a probability of x being really between mu minus sigma and mu plus sigma. And now we have mu here and we have sigma here. Yeah, so it's going to be probability of x being between mu minus sigma and mu plus sigma. So it's going to be integral from the first one, whatever it gives me as a decimal, to the second one, whatever it gives me as a decimal, 5x to the power of 4 dx. So after I calculate it, I get 0.718 to 3 significant figures.